It is my pleasure to introduce Peter Jipsen. He's here from Chapman University, and it looks like the title on his talk there is the same as in the program. So this is always a good thing. So not necessarily if it bad thing if it wasn't, but structural results about involutive residuated lattices and involutive Poe monoids.
Thank you. So sorry to the online people now. I hope you can hear me. So I'm talking about the joint research with Jose Gilfres and Sid Lodia. Sid is an undergraduate student, and Jose has joined Chapman a year ago and was instrumental in making these results become the reality that they are now in the last couple of weeks. And so to start with, an involutive residuated lattice, normally I would say it's a lattice and there's a residuation on it, and then that the residuation is involuted, meaning that it has two linear negations that are defined from the residuals. But it turns out that there's a simpler definition, which is at the same time much better for what we're trying to do here, and also very closely connected to lattice ordered groups. So the name that they go under in this much shorter definition, involutive semi-ring, is also indicative that the semi-ring structure in the background. So it's an algebra that has a join, a multiplication, an identity, and two unary operations, tilde and minus, or left and right linear negation, or involutive negations is what we're referring to them here. And so the structure is simply a joint semi-lattice, so it's ordered, and it's a monoid. So it's not quite a lattice ordered group yet, because if I said here group, then that's what it would be if it had to be order preserving. But instead we just add this axiom, which says that the order is equivalent to either one of these two conditions. And from this, you can deduce that the two unary operations are order reversing, and that they undo each other, so that the tilde minus is the same as the identity if you do both of them, and the same for minus tilde. And then it means that you can define a meet, because the unary operations turn the lattice or the semi-lattice upside down. And so you get a meet on the same order, and that's a lattice. And in particular, it doesn't matter that in the definition here we used -1 instead of tilde1. They turn out to be the same, and they will be denoted by 0, as is traditional in residuated lattices. And also we leave out the dot, of course, when we write terms. And the class of all these involutive residuated lattices, as I will refer to them in this talk, but if I were giving a computer science talk, I might call them involutive semi-rings. It's the interesting thing is it's a variety. In spite of the fact that this property here is not equational, it can be translated into some very short, simple equations that you don't use in practice, so it's not worth writing them down. But the point is that it includes all lattice ordered groups. So it's a generalization of lattice ordered groups. Every lattice ordered group is an involutive residuated lattice. And the way you get to lattice ordered groups is just the two unary operations are the same, and they're actually the inverse. And so that means that when you calculate this 0, which is -1 in our notation, it's actually 1 to the inverse of 1, which happens to be 1. So in groups, in lattice ordered groups, the 0 and the 1 are the same constant element. The constants coincide. Now is that the difference in this talk for lattice ordered groups, we wouldn't be able to do this, but in involutive residuated lattices, the identity can be the top element. And in that case, we call them integral. And then in that case, 0, which is the involution of the identity, either the minus or the tilde of the identity, is going to be the bottom element. And so you get an ordered structure which is bounded by 0 and 1. I need to move on because we have a few slides to get through. The examples of involutive, of integral involutive residuated lattices, there are lots of them. They're easy to construct, and what's relevant to this ordered structures meeting mostly is that we can construct them from an L group, and we can do it by taking the identity of the L group as an element, and then the interval to any element Z below that. And if you restrict your operations to that interval in a suitable way, you get a integral involutive residuated lattice. And this restriction is sometimes, well, generally in the commutative case, it's referred to as the Mundisi functor, and it's also, you know, a composition of a negative cone nucleus and the Z cone nucleus, which is the filter above Z restriction. And what you really do is you call the 0 Z, you redefine your multiplication, which could go below Z as something that is just going to stop at Z abruptly. You force it to, everything gets joined with 0, and then you define the tilde and the minus in this way, showing that they don't have to be the same if your group is non-commutative. And so that's a standard way of constructing something that is called a pseudo-MV algebra, which is something that Charles Holland investigated a lot in the last few years of his research. And so this is where they came from. And if you started with the integers, you got what are called the finite Lukasiewicz chains or MV chains, denoted by Ln. L2, for example, would be simply the Boolean algebra and will play a role in this talk. And the Chang algebra is something that you would get from a Lex product of Z with itself, and then using the element Z from that Lex product as in the next factor down, you pick the identity again. And that algebra in MV algebras has a special name called the Chang algebra because it has infinitesimals in it. But anyway, it's a very nice infinite algebra. One can construct many other integral involutive residuated lattices from things like rotations and products. Just taking products of integral algebras remains integral. But the problem is there's no full description of all of them. I mean, they include L groups. And sorry, no, the integral ones are not L groups. But even in the integral case, this restriction, they come from pieces of L groups, which can be complicated. And in general, they can be even much more complicated. But they're a well-defined class. Now, what are we interested in this talk? I'm going to show you how to construct non-integral involutive residuated lattices from integral components. So even though we don't have a good classification for all the integral ones, we actually, in a certain subvariety of involutive residuated lattices, know precisely how to construct the remaining ones of that subvariety from these integral components. And this is the new result. That's how you can, in this large subvariety that will be properly defined, you can get all of the algebras from the integral building blocks, and it produces a full structural description of these algebras. And the interesting thing is that it generalizes a presentation that I mean, some research from a couple of years ago with Olem Tait was a graduate student at the time, and Diego Veloto was here as a postdoc, came to visit me for a month, and we figured out this structural description for the case where every element in the involutive residuated lattice is idempotent. So the restriction was very severe. We assumed that x squared is equal to x for the monoid operation. And in that setting, it was, after a lot of work, possible to see the structural description, but in a weird way that, I mean, the paper is great. You should look at it, but the description I'm giving today is simpler and much more general. So it's just that I don't think we could have found today's description without having done that previous research of figuring out how it works. And in the case of these integral, in this restricted case, when you assume idempotence, the integral components are just Boolean algebras. And we restricted ourselves to finite things because we wanted to see how it works. We we're looking at finite Boolean algebras and how they get patched together. And so that's, this finite 2-element Boolean algebra can be used to build non-integral things that looked very nice. And in this present setting, we don't have this description. So there are some details we have to go through, but let me see, maybe I can skip ahead here, show you some picture. I should have put it earlier. There, for example, is a generic construction of one of these non-integral guys. So we have an index set, which is itself a joint semi-lattice called D, because it turns out to, in many cases, be a distributive lattice. And then we have the components. These are integral components in this picture. I have 4 components. You can see they're integral because they have 1 at the top and 0 at the bottom. And then the ordering on this is constructed in a certain way that makes a nice algebra. And the identity now sits here with its involution 0 below it. So the algebra that we built is not integral because it has other stuff above the identity. So, but this is pretty much a generic thing for this very simple case, but the D could be an arbitrary joint semi-lattice with bottom element 1. Unfortunately, the identity is denoted by 1, but it happens to be the bottom of D. So let's go back and see what the details are in doing this composition. And I should mention that one of the important parts here is right at the beginning of this definition. The order, and this is true in any residuated lattice, but hasn't been exploited enough. The order is completely determined by this condition. And this condition has the monoid operation in it and some subset. You need to know the subset of all the elements below -1. But if you applied tilde to both sides, then the inequality would reverse, and it's really just saying you need to know the positive cone and the monoid operation, and then you can get the order operation. So we're going to construct this, we're going to build the bigger algebras by constructing the monoid operation and having a good idea what the positive cone is, and then the ordering will come from the fact that we want this definition to hold. So here we have first of all, an observation. So this was the last slide that I went over. So here's the next slide. We have this concept of locally integral involutive residuated lattices. And these are algebras that are constructed from integral components by 3 simple equations. The first equation is telling you some nice interaction between the 2 different unary operations. Here's the second equation. It's a bit weird. It's just the shortest version of it. It says that the elements that are below 0, these elements of the form x meets 0, have to be square increasing. When you square them, you stay below 0. It's enough to assume this part. And then this third equation, I mean, I wrote it as an inequality, but it can be rewritten as an equation if you have a join. The third equation has to, well, it's called square decreasing. It's very common in residuated lattices, and it's a weak form of idempotency, of course. It has to apply everywhere. The interesting thing is that the 3 equations together is what allows us to do this decomposition. And so this variety of locally integral involutive residuated lattices is where the decomposition works, and it's a vastly bigger class than just the integral ones themselves. And if you have an integral involutive residuated lattice, it's already in this setting, it's locally integral, right? So these are part of the variety, and that the main result that we'll get to after some details is that you can do this, you can build the remaining ones as a disjoint union, as you saw on the picture. So the other realization is that everything works without the join semi-lattice. So the result applies more generally to something called partially ordered, involutive partially ordered monoids, or in short, they're called IPO monoids. And what are they? They are simply a poset and a monoid on the same set. And then this condition again, which doesn't reference the join. So they're more general than involutive residuated lattices because they allow a base that doesn't necessarily, where joins don't exist. In the, we also have the notion of integrality here. And in fact, the MV algebras as a class, you don't need the join in the definition. The join and meet in MV algebras is a consequence of something that it looks like this. You just need to add another axiom that doesn't reference join or meet, which I haven't mentioned here. But also the class of IPO monoids is much bigger. It includes all groups. It's really the generalization of group theory to ordered structures. And so groups are obtained if you just restrict the partial order to be the identity relation. You get ordinary groups. And if you keep it as a partial order, but you agree that tilde and minus are the same unary operation and force it to be a group theoretic inverse, obvious equations have to be added here, then you get partially ordered groups. So we went from lattice ordered groups to partially ordered groups, but we're doing this in a more general setting to see a nice structural decomposition result. That was the introduction. Now I have to get through some details in half an hour. So let's see how it goes. The details are a bunch of lemmas. Each individual lemma is actually easy to understand and relatively simple to prove, which is different from what we did earlier with Olin and Diego. In that paper, we were in a much more restricted setting and we forced the result through, and the proofs are not particularly intuitive and technical because they're just algebraic. Here, because we have a simpler axiomatic setting, things go relatively straightforwardly. An IPO monoid from this very terse definition already satisfies a lot of nice properties. I already mentioned this. It's true in this general setting as well. The most important identities are here. This rotation tells you that if you have x times y below z, you can move the z over the less or equal to, and it becomes a tilde z. It pushes the y into the first position, and the x moves across, and it becomes a tilde x on the other side. So this is a nice rotation axiom. And you can go the other way, but then you have to use the opposite linear unary operation, the minus. And then it follows that you have antitonicity. That's very easy. You just plug the identity in for one of the three variables in the right place. And you do residuation. Well, you get residuation from the rotation axiom by applying minus to this equation. Then you get x on this side is less than minus the remaining part, and this is now the residual. It's how the residual is represented in involutive residuated lattices. And the constants are related in the way that you wish. So here's the equations for the residuals to convince you that we're in the setting that I'm normally in, but in a slightly more convenient signature. And then we have these lemmas. So for example, this property turns out to be true in all involutive partially ordered monoids. And it's an important property because it tells us that the kind of things that we would expect from De Morgan's laws coincide in an interesting way in this theory. And so the second property is that the idempotence of a tilde x is equivalent to the minus x being idempotent. And then, well, for the first part, this is really a standard result. You could look in the book on residuated lattices. And for the second result, you can use part one in the middle here, and you just compute. You multiply minus x and minus x together. You put the minus tilde in front of it, and now you replace this tilde outside and two minus signs inside. that's this term with x in both variables. And then you replace it with the other term. You get two minus signs in front, but we assumed that tilde x is idempotent. And so we just get tilde x here, and then it simplifies to give you minus x. So it's proofs like that show you how these interact. Here's another lemma. If you have minus x times x, if that's the same as x times tilde x, then you can put the tilde on the left and the minus on the right, and it also has to be equal. It's not completely obvious why this is true. Initially, I used true benign to prove this, only to then discover that it's a 3-line proof, right? I mean, not for proof benign, it's like a 60-line proof, but if you analyze what it is, it's very simple. And of course, one should have done this by hand to begin with. I'm not going to look at the exact details, but again, it makes use of this identity that I mentioned here about how tilde and minus are related in a term with multiplication. The positive elements are very important because that's the positive cone of an involutive residuated lattice. And so that's the name A plus is standard in residuated lattice theory. And using the residuals, we can say that this equation that we just saw, which is not always true, what it really says is that x under x is the same as x over x. So it's imposing some regularity on our algebra. And it's sort of making things balanced. And so we also, this is very standard that if you have an identity element, 1 times x is x, and then we can residue it by dividing with the x on the standard side, and we see that 1 is below x over x. And so all these terms here are actually above the identity, so they're in the positive cone. And these terms are important enough in our discussion that we give them a name. These are the local identities. So 1x and 0x are these two terms. And you can, if you assume this identity, then you don't have a bias in how you define them with tilde and minus. So that's one of the reasons we need some identities here. So if we assume this one, that seems to be enough, then we already can tell that 1x is correctly connected to 0x in the standard involutive way. Now, an IPO monoid is called integral if x is below 1 for all elements x. I don't have a join, so I can't express it with an identity, but it's called a inequality it's a universally quantified inequality, and the theory of IPO monoids is not, we're not talking about varieties, we're talking about partially ordered varieties. So since these two operations, tilde and minus, are dual isomorphisms of the lattice structure, I can deduce that 0 is less than x, and the IPO monoid is locally integral if it satisfies these three properties. The first one is this balance, from which we can deduce that if we put a tilde on the one side and a minus on the other side, we're also still equal from a previous lemma. We assume square decreasingness, and then we assume a quasi-equation here because we can't express it as an equation, but it's also clearer what it's saying. It's saying that all the elements below 0 have to be idempotent. So there's some idempotence restrictions, but it's not on the whole lattice, on the whole algebra, it's only on a small part of the algebra. And every integral IPO monoid is locally integral. We saw an argument, well, I didn't explain the details, but it's very easy to see that that works. Now, more details. Define A sub x to be all the elements where 1x is equal to 1y. So all the elements which have the same local identity. This is actually an equivalence relation, and A sub x is an equivalence class. You can also define it using the 0. That's not the local identity, it's the local 0. Same thing. And then you have some technical properties that you have to check. And all these proofs are very straightforward. I didn't put them in here, but they've been very carefully written up, mostly by Jose and by Sid. And so for example, if you take the local identity, if you take the local 0 of tilde x, that's the same as the local 0 of x. So x and tilde x are in the same equivalence class, is what that will tell you. The notation, interval notation is standard. So 0x, 1x is all the elements in between. That's not the equivalence class, but it turns out to be an important set, and x is in there if you're using the local 0 and the local identity of x. And then there's a characterization here that we need, some other properties. The last one is the most important. It tells you that an element is in the equivalence class if it is inside this interval of the local x, of the local identity and 0, and the local identity has to act as an identity on it. So it works nicely, because what will happen now is that these equivalence classes A sub x are going to be our integral algebras from which we build the whole thing. Now, this is here again explaining that the A sub x partition the algebra A, and the A will be a locally integral IPO monoid. So, sorry, if we start with 1, then for all positive elements of A, the positive element will be equal to its local identity always, and this is actually a characterization of when you are positive. And an element will be below 0, so down arrow here means the principal ideal, or everything below 0, if and only if the element has, if the element is equal to its local 0. So what this important lemma is telling us is that the positive cone contains exactly the local identities, and the elements below 0 are exactly the local zeros in such locally integral IPO monoids. For every x in A, 1x is the only positive element of AX. So that gives us a canonical representative for the equivalence class. And from now on, we will use that. And it shows us that the equivalence classes are indexed by the positive cone. So that's nice. And that happens as soon as you have the axioms of local integrality. Locally integral IPO monoids have more properties. A sub p, now I'm using p here instead of x because p is a positive element. I can always find this positive element, and that's the index. The set is closed under tilde and minus. It's closed under non-empty joins if they exist. So of course, if you have a poset, sometimes the joins exist and the set will be closed under those. And it's closed under non-empty meets if they exist. And it's also closed under multiplication. So of course it has an algebraic structure, and that's what this theorem is saying, that the structure of the set that we have isolated now is an integral IPO monoid, where these operations are the restrictions of the big algebra. And if A is a locally integral involutive residuated lattice, so if we have all joins and therefore also all meets, then the resulting algebra that we get is an integral involutive residuated lattice. And these AP algebras are called the integral components. Now, I think we're on time here. I'm not going to drag you through this proof, but I wanted to show you that while this might not necessarily be the proof that you would find yourself, it's not technically difficult to check that this proof is correct. And what does it say? All positive elements of a locally integral IPO monoid are central. Central here means that if P is a positive element, Px is equal to xp for all elements of the algebra. And so you have to check that this is true and that this follows from local integrality, which of course it doesn't have to be true in general, but it is true in the subvariety. And it uses the rotation axiom. many places, as you can see. Right? It's just I should also mention that relation algebras are involutive residuated lattices, and Nick Galatas gave a talk about weakening relation algebras yesterday here at the conference. And while these results don't directly apply to them because they're not locally integral, there's likely to be a generalization of what I'm telling you today that will also include them in some way. So, this is a very interesting theory that we're in, because it sits above a huge variety of algebraic theories that includes the partially ordered groups and relation algebras and almost all the algebras of algebraic logic that have been investigated for quite some time. It's a theory that currently we've only investigated when we have involution, but there will actually be a generalization of this that handles aspects in the non-involutive case. We just haven't been able to find the time to work out the details there, because we first would like to know how all of this resolves. Products between components and distributivity are handled here in this lemma. Given a locally integral IPO monoid, if you have two positive elements P and Q, and two other elements X in AP and Y in AQ, then the product will be in APQ, where P times Q is computed in the big algebra. So the product in the positive cone tells you how that works. And what's interesting, because everything in the positive cone turns out to be idempotent. Now, our assumption of local integrality is that everything below 0 is idempotent. But in this theory, it turns out that if you flip over with using one of the linear negations, this forces everything in the positive cone to be idempotent. And the other direction actually doesn't work in general in residuated lattices, but this is the way we need it anyway. So this P times Q is actually the same as P join Q in the positive cone. And that's important because the positive cone is a joint semilattice. And so that's where this index joint semilattice actually comes from. So by duality, YZ below 0 will imply that the product below 0 is the meet, because the involutions, the minus operation, is a De Morgan operation on the lattice. So it turns joins into meets and produces this surprising result that the joint semilattice is, in fact, if you start with the IPO monoid, the joint semilattice is flipped and reflected as a meet semilattice in the bottom. It's got a top element. It has all meets. Therefore, in the finite case, all joins will exist. And so if you restrict to the finite setting, then it will be a distributive lattice. So here I should have included the word finite somewhere. Apologies, that's a mistake. In general, it doesn't have to be, but it's a joint semilattice with a top, and we're still figuring out what it is exactly. Now I have to tell you something about Plonka sums, because that's actually the construction by which the monoid operation from the components is used to construct the monoid operation of the whole algebra. So you start with an algebra, you identify the components, and now we want to build the algebra back from the components to show that we fully understand the structure. Well, you need this idea that goes back to Plonka in the 1960s. A family phi ij of homomorphisms is, compatible, go away, if for every I in capital I, phi sub I is the identity on the ith component, and if I is less than j less than k, then there has to be a nice composition between these homomorphisms. So the components are connected by certain homomorphisms, then we call them a compatible family. So this compatibility is defined right here. And if you have a compatible family of homomorphisms between algebras, then you can, and they are indexed by a joint semilattice, which has to have a bottom element called bottom here, then you can construct the Plonka sum as the disjoint union of your components. And now we have to define the operations on this. This can be done in general for any signature. We only need it for the monoid operation, but if you have an n-ary operation symbol in general, and you take n elements from your components, from the components I1 up to In, then you want to define the operation on these n elements, but they're in different components. So what you first have to do is force them into a single component J, and that component is identified by the join in the index set. And then you use your homomorphisms to push everything into this one component, and there you have an operation that is from your signature, and that's how you define the operation on the whole algebra. And this construction has shown up in many different places, and this is a categorical description, so it's a very categorical construction. This property of compatibility is just saying that the family is given by a functor. The compatible maps between components, well, if P is less or equal to Q and both are positive, then we can define a family of homomorphisms from the component P to the component Q by simply taking any element X in the component AP and multiplying it with Q. That's it. That's the connecting homomorphism. And this map, you first have to check that it is well defined and that it respects the monoid operation. So to see that it respects the monoid operation is very easy, because if you have X times Y and you pre-multiply that with Q, Q is idempotent, so you get to replace it by 2 copies of Q. And Q is central, so you get to switch the QX in the middle, and now you have what you wanted, right? So it's almost tailored to work. Of course, we didn't say centrality in the assumptions of local integrality, but it turned out that local integrality forced centrality on all of this, on the elements in the positive cone. So now we have the main theorem, the structural characterization. If you have a locally integral IPO monoid, and you have a family of monoidal homomorphisms as before, meaning defined from the algebra A by multiplying by a positive element, those particular families phi sub PQ, and then you construct the Plonka sum over this family of compatible monoidal homomorphisms, then you can define the tilde on the whole structure. S here stands for the big structure, which is the disjoint union of all these components. You can define tilde on it by just saying it's the same as in each component, because the components are disjoint and they each have their own tilde. So unary operations just glue together in this very simple way. But for the multiplication, you need to use this Plonka idea that if you want to multiply 2 elements from different components, you first have to push them into the same component and multiply them there. But this is possible because our family is compatible. That's what the previous lemma said. And then comes the magic that you define the order on the whole thing by multiplying the way you want. Namely that X times the tilde of Y in this new structure S, where both of these things have now been defined, should give you the 0 of the, sorry, this should not be PQ, this should be just the 0 of Q, I guess. So excuse me, a couple of typos that we have to take care of, but I'll put the revised notes, slides out if you're interested. And then the conclusion is that this disjoint union of the components is A. It's not isomorphic to A, it is identical to A. It is exactly the same thing as A. You've reconstructed A from its pieces. If A is an integral residuated lattice, then all the pieces will be integral residuated lattices. And what you're reconstructing, this partial order, will be a lattice order. And if it's commutative, well, it'll be commutative if and only if the components are commutative. And in fact, this last observation is true for many other identities. Plonka sums preserve what are called regular identities, and you can replace commutativity here with any regular identity, and it will be preserved from the components to the whole algebra. Regular just means that the identity has all variables that appear on one side also appear on the other side. So it's a mild restriction. There's our generic example. Everything works as you like. The example is not super generic because there will be connections depending on the homomorphism. Sorry, there will be connections here and here and here, which the picture doesn't show. And these are then reflected down here. So there are very interesting lattices that show up this way. And so to see more examples, here's one. If you take an index set, which is just 3 elements, one above the other, the bottom has to be the identity, so we're calling it 1. And then we have P and Q. And now I'm going to take the standard MV chain. I should have made it orange here as well. So here's an MV chain. Here's another MV chain. What is the standard MV chain? It's just you take the real numbers and all the elements between 0 and 1. The way I talked about the Mundisi functor, you should really take the elements between 0 and -1, but you can, the standard one is defined on the unit interval, and the operations are then just the dual operations. And now you have 2 such copies, and you can define a connecting morphism, which is just going to map the first chain to the top element of the second chain, and so on. We would, in order for this to be correct here, you'd have another such morphism from here. All of, yes, I guess I should have drawn this part here as well. And then you do the Plonka sum construction and you obtain this algebra here, which has the identity right there. So it's not integral. But what is it actually doing? It has an interesting subalgebra. These 6 elements are called the 6-element Sugihara algebra, which is an algebra of relevance logic. The relevance logic Rm sub T is a well-known substructural logic that is based on the variety generated by all the Sugihara chains. And here we have MV, which is another well-known substructural logic, which is used for fuzzy logic applications. So relevance logic and fuzzy logic have not really been combined in a single algebra in a sensible way so far, but here's an algebra that does exactly that. There are relevant aspects of the reasoning that happens in the positive and negative cone, and inside you can use fuzzy logic on the components. So we're still claiming there will be applications. I'm pretty sure. I mean, people have done this. They've invented 2-level logics just to combine logics, but here we're doing it in the same algebra. Another interesting example is if you don't use Lukashevich algebras for both. So here we have a Lukashevich algebra L3 and an IMTL algebra, which is more general. It has an idempotent in it. Then you can map parts of the first component to the idempotent, and the 1 has to always map to the 1 by this connecting morphism. So now I have a very simple example. I'm just combining 2 lattices, 2 chains really, and I get something that on the interesting effect here is that here's my component, but the component can be intertwined with another component in the order, not necessarily in the lattice, because this is a lattice, and under joins and meets, these are closed individually. But the order is doing something that at first, when I saw this example from Mace 4, I had computed it already. I was like, uh-oh, our decomposition isn't going to work for this guy. And then it turned out, no, it works perfectly if you look at it the right way. And it recreates. So from these 2 chains, this gets recreated. And many more complicated algebras show up like this. Here's an interesting question. How many of these small finite IPO monoids can be constructed from components? So when you calculate small models, you can see that the integral IPO monoids, the ones that we don't fully understand the structure of, there's lots of them on 9 elements, 145 up to isomorphism. But the locally integral ones, there's a lot more of them, 448. And these 448 are constructed from these smaller integral ones. And you can really figure this out almost by hand. I mean, at least up to the level of 9, I've done it by hand. These 9 are constructed from these, and these we all know very well. One of the 4-element algebras is the IMTL algebra you just saw on the previous page. The others, there's a Sugihara algebra and there's a Lukashevich algebra. So these are the components. If you do this with integral residuated lattices, well, it's still quite impressive because in order to not be a lattice, you have to have at least 6 elements. It's something that has a top and a bottom, and then in the middle you have to have a 4-element crown. That's the smallest poset that's integral and gives you a component, and it shows up right here because we have 13 IPO monoids and we have 12 integral residuated lattices on 6 elements. So one of them must be not a lattice. And to compare this to what we knew previously, when we didn't have this nice perspective, well, if you have Boolean algebras, the spectrum, the fine spectrum of them is very easy. There's 1 for every power of 2. And if those are your components, then you can only explain the structure of 10 9-element ones. But with the current theory, we can explain the structure of 440. Okay, I'm just trying to show these numbers because we know the numbers. Nobody would. It's not about finite algebras. The important difference is really that the previous result was about finite, totally idempotent algebras, and now the finiteness restriction has been removed and the idempotence has been removed, and it works surprisingly in a simpler way. So what we still want to address in a nice way is if you're just given a compatible system of morphisms over a joint semi-lattice indexed set, what are the conditions that have to hold so that the construction that we just went over will produce a locally integral IPO monoid? Because we don't, so far, I haven't told you anything about that. I've told you if we start with a big algebra and pick out all the components, then we can reconstruct the big algebra from the components and from the connecting morphisms. That was what we did so far, but there's a more general aspect to this. You can be starting with components and a system of maps, and they have to be compatible. So you better take a compatible family, and then you can define the structure, which we denote by the integral over the family of these components. This is in category theory, pretty standard notation for the Grothendieck construction, because you're summing up all these pieces, right? And in the infinite case, you can even think of it as an integral, but it's a very big generalization of the notion of integration. You take the Plonka sum here, you do exactly what we did before. You define the minus and tilde the way we did before, and importantly, you define the order in the same way. And then you call this a gluing, right? And of course, the components that you're going to try and do this with should be integral, but it's not always going to work. We want to know when does this result in a locally integral algebra? And there are 3 conditions. The first one is pretty clearly connected to this notion of being balanced, because here we have a times the tilde and then minus the other variable times a. So it's called balanced. The second condition has to do with the 0. It's very interesting. If you have distinct P and Q, then the morphism cannot send the 0 of P to Q. It has to avoid doing that. So these are not 0-1 homomorphisms. They only preserve the 1 and the multiplication. They are monoidal homomorphisms. And they must be not 0 preserving homomorphisms unless P and Q are the same, in which case they have to be, because they have to be the identity. And then you have the condition that we would dearly love to replace with something simpler, the transitivity condition of the order. Currently, we're just assuming it. And you can check it, of course, in the finite case, but we would prefer to have something simpler here. Finally, we have the main theorem, of this gluing result, if you have a lower bounded joint semilattice, a family of integral IPO monoids, and a compatible family of morphisms that satisfies the three properties from the previous slide, then you can do this. And it's if and only if. That's the crucial part. Some details to check, so the preprint should be available soon. Some questions at the end here. Can this transitivity condition be replaced with something local about how the maps connect? Find conditions that ensure that the algebra that you construct is lattice ordered. Of course, just check it's lattice ordered after you've constructed it. If it is, it's a residuated, involutive residuated lattice. But again, it'd be good to have a more local condition. And an interesting question, whether the subvariety that we've identified has a decidable equational theory. Unclear. It's got, I mean, the three axioms were fairly straightforward, but even in the case of assuming just total idempotence, I don't know the answer to this question. That's it. Thank you very much.
All right. Do we check? Does anybody have any questions for the speaker? Okay, I'm going to ask a stupid question because this is not really my strength in understanding these. You know, you know me, I'm a little bit better with the lattice ordered groups and stuff. But so this idea of these finite involuted residuated lattices, and then you're using these to create these other things. And then you mentioned this 6.1, the two crowns.
Right, Sugihara.
Could you, like, just to give me a sense of, that's the one?
Yeah.
Okay. So when I look at that and I'm thinking that's somehow this involuted residuated lattice,
Yes.
This just the 6 points, right?
Just the 6 points, this one here, yeah.
And I pick a point and then I'm like, I'm supposed to be able to know that I can do a tilde. And
Yes,
I can do a,
yes. So tilde and minus in this case coincide, and they connect, they just flip the thing upside down. So tilde or minus flip things.
Gotcha.
So in that, I mean, think about it like this. Lattice ordered groups have 0 and 1 equal. So stuff gets collapsed. If you tease this apart a little bit, what do you get? You get a lot of finite models. You get some beautiful lattice structure. None of these lattices, I mean, sometimes they're distributive, like this chain here is a distributive lattice, but it's almost accidental. What you're looking at is not a distributive lattice. So you get a lot of non-distributive models showing up because we've enlarged L groups, right? But what you know about L group theory can be done in this larger theory, because this larger theory is the theory of groups on partially ordered sets. Lattice ordered groups are the theory of groups on distributive lattices. That's a vastly restricted thing, with the additional restriction that 0 and 1 are the same. So I think what we're learning here is that all your knowledge from L groups can be lifted in some way, not everything, of course. Yeah. And what do you lose? You lose some connections to automorphisms of chains, which are really just L groups, right?
Right.
But you gain this landscape where your techniques will still work. That's what I'm excited about.
Cool. Any other questions? Oh, wait.
Yeah, actually, I was wondering like whether there exists some topological characterization of the like structure what you already talked about. And another question is that did you already looked at the corresponding logic and the completeness and soundness in some sense?
Yeah, I mean, the locally integral, the second question is easy. Locally integral involutive residuated lattices are the algebraic counterpart of a very specific substructural logic that previously hadn't been recognized as being of central interest in this area. I think that's what these results are saying, that these three axioms of local integrality are very interesting and important, because they can show you how things are You know, it reduces the structural theory from the general case to the integral case. That's what the results I talked about do. As far as topologizing this, there's an easy way to topologize orders by looking at the downsets of an order that's called the Alexandrov topology. And so posets lead to very easily understood topologies. And I would think that that's relevant to answer your first question, but I don't understand the details there. And there's a lot of interesting work that can be done. So thank you.
Okay, let's, oh,
I have a question on a technical notation there in the Poincare sum.
Yes.
That there is the order of the indices there in the when we compose the morphisms there.
Yes, correct.
Is this like uncompromisable order? It has to be like this, or
No, you can.
in a sense, could we write these two the other way around?
We certainly could, and
Yes,
I
good,
think it
good.
would simplify things. I'm not sure what.
Like phi ij and then circle phi jk will still be phi ik.
I guess we chose the. I mean, you're doing two things here, right? Phi ij is the map from AI to AJ. Very nice. Not so nice. Now you want to switch it. Very nice here. Maybe not so nice there, but it's, you can turn the whole. Instead of talking about the joint semilators, you could talk about the meet semilators.
I see. Oh, right.
It's another option. So.
Very good.
Poincare has a lot of variations, and they all work.
Yeah, the reason why I'm asking that should probably be clear after my talk.
Interesting. Thank you very much. Yes.
Thank you.
okay, let's thank the speaker again. And unless there's any issue, how about we start at 10:36, which is in like 3.5, 4 minutes? That should be enough time.